Thank you.
Well, hello everyone. For those who don't know me, I'm Juan Manuel Catalán, as Manuel said. And today, well, I'm going to present part of the work of my PhD thesis, which has been done under the supervision of Professor Oscar Flores and Professor García Villalba. And it's entitled Anesthesia-Dynamic Effects in Bio-Inspired Problems. Okay, so first of all, a little bit of motivation. Why are we interested in studying bio-inspired problems? Well, we know that atmospheric flows typically are not laminar. Also, looking at swimmers and flyers usually in nature, we know that they benefit from fluid-body interactions, triggering the unsteadiness. Okay, and also even that some trees take advantage of wind and turbulent gas to disperse their seeds. Okay, as we have here some examples. Okay, thanks to their suitable shapes, so we know for sure that nature is wise. We'd like to deepen in the understanding of the physics behind these kind of problems. Okay. So how do we do that? Well, we propose to perform direct numerical simulations, the Navier-Stokes equations for incompressible flows, and we basically account for the fluid-body interaction, adding a source term to the Navier-Stokes equations. Okay, basically uses the inverse boundary method. Okay, we solve them using a fractional step method, Runge-Kutta, which is semi-implicit of 3 stages, central finite differences of second order, staggered Cartesian grid for the fluid, and Lagrangian grid for the body. Okay, I have here examples of these grids. Traditionally in our group there have been two main developments. Okay, first of them was Toucan, which was originally developed by Dr. Manuel Moriche back in 2017 and later extended by Dr. Alejandro Gonzalo in 2018. This is a CPU-based solver. It's extensively validated up to roughly 8,000 processors. It's Fortran-based, uses MPI for the parallelization, iPref for the iterative solvers, and HDF5 for the input-output. And recently, Manuel Guerrero and myself have developed a GPU version of a GPU-accelerated solver, somehow an update of this previous one, which is a Python-based solver, uses CUDA NumPy, CuPy, and HDF5. Okay. In the following, I'm gonna give some details about the new solver. Okay. Basically, Toucan GPU, we have developed it to have 2 branches. Okay. First of them is a 3-periodic branch, which is very suitable, or is suitable for the research line of cardiovascular flows in our group. Okay. And the other one is one in which we have 2 periodic directions and one that is non-periodic. And this one is more suitable to aerodynamics, okay, or this kind of problems, not only, of course. In here, I'm just showing some verification that we did with Toucan, okay. Basically, we compare the 2 solvers in here. We select a case, which is the flow around a fixed and a moving sphere at Reynolds 200, okay. Basically, we select some initial condition, stringwise in the stringwise direction. Also, direct boundary conditions for the inlet, advective for the outlet. We select homogeneous Neumann boundary condition for the pressure. Okay. In here, I'm displaying here some instantaneous results of stringwise velocity. Okay, and the error of stringwise velocity. Basically, the message here is that basically when we compare the errors, okay, absolute errors in this in all the components, in all the velocity components, also the pressure, we are basically getting errors, absolute errors between the solvers of 4 to the power of -8 and -10 for the Eulerian and Lagrangian variables respectively. And this is actually after 140 physical simulation times, so this is quite a lot. So we consider this is verified, the solver works, and now we take a look to the performance of the solver. Okay, for this very same problem, the flow around a fixed sphere in this case, this is a small problem. Okay, as you see here, 256 times 128 square. And basically here I'm plotting to measure the performance, the wall time per delta t of the simulations, okay, comparing the GPU and the CPU solvers. In the CPU case, we are using the cluster, the mid-size cluster of the aerospace engineering department. For the GPU, we are using, in this particular case, a Titan V NVIDIA GPU. And basically we see as we increase, for this particular problem, as we increase the number of processors, basically we reach a point in which the, sorry? Sorry for that. In which we lose parallel efficiency much before reaching GPU performance, okay? For this particular case, again, the GPU is at least 25 faster than 64, at least 64 number of CPUs, okay? Again, for larger problems, this is expected even to be higher, okay? So this is a great milestone. In this thesis, on the other hand, we are interested in studying perturbed flows, okay? And the way we propose to do it is basically by adding a source term to the an additional source term to the Navier-Stokes equations, okay? Which is this FST that I mentioned here. Basically, by including this term, we inject fluctuations, okay, of a typical size, that is the integral scale, and an intensity, okay, also and a time scale. These fluctuations are three-dimensional, okay? Basically, they are correlated in space and time. And in order to generate them, we employ a well-established approach in the literature, which is a digital filter approach, okay? There is another approach that we actually use that is a that is a passive grid approach that we employ to generate turbulence downwards this grid, okay? I'm gonna talk a little bit about some applications that I've been doing during my thesis, okay? For this, I'm gonna explain two applications. I'm not gonna give a lot of detail on them because I want to extend the last one a little bit more. The first application is the free string turbulence generation at low Reynolds number, okay? And here basically we are comparing these two different approaches that I mentioned before, synthetic turbulence and grid-induced turbulence, okay? Basically I'm here just showing some instantaneous results, three-dimensional, okay? Basically in this study we compare these two turbulence generation approaches in terms of energy spectra, isotropy, characteristic length scales, decay of the turbulence intensity, and so on. I'm gonna stop here because otherwise I'm not gonna have time for the rest. The other approach that I've been spending time in the thesis is the motion of a spherical particle settling in the presence of ambient flow perturbations. In this problem, basically, we analyze the effect that perturbations of different size and intensity has on the motion of a particle that is settling under the effect of gravity. Okay, so in here the particle is free to move, and basically we assess how these perturbations in the free string affect the motion of the particle. Okay. So the last problem that I've been dealing with, and that actually that I'm spending time right now, and it's the last part of my thesis, is devoted to assessing the aerodynamic performance of a bioinspired microscale wind turbine. Okay, this is a fluid structure interaction problem in which basically we need to couple Navier-Stokes with rigid body dynamics. Again, we are using here inverse boundary method, okay, with our brand new solver. Basically, I display here a model of the rotor, okay, in which we have a blade, we have several reference frames, we have a free stream velocity, okay, and we basically select the system to have 3 degrees of freedom, okay. First of them is the rotation of the blade around an axis of rotation, and then there are 2 additional rotations around a joint, which is this joint J, okay. So basically these 2 angles, or these 2 rotations are a pitching angle, okay, which are displayed here, this theta, and a coning angle, which is this one, okay. So this is gonna be our model, okay. Basically the idea is that we're gonna be extracting power by, since the idea of this is by inspire, okay, I'm gonna give more details now, but this is gonna auto-rotate, okay, and we're gonna extract power by putting a braking torque to the system. And we are gonna just compute typically the power coefficient, okay, based on this power. Of course, since this is coupling the fluid and the rigid body dynamics, the aerodynamic forces are gonna enter here in the right-hand side of our dynamics equation, okay? The same for the braking torque, of course. We have selected a preliminary configuration with a mass distribution inspired on a real winged seat that I have here, okay? This is equivalent to basically having a blade that had uniformly distributed mass, okay? And also we have placed 2 point masses, one in here, which is P1, that is sort of acting as this nut of the seat, and another point mass that we have put here that is sort of the leading edge rod, okay? If you see here, this has sort of an structure here plus the point mass. So we're trying to mimic somehow this behavior in a preliminary way, okay? And we have, of course, computed the inertia tensor based on this mass distribution, okay? For what regards the computational domain, we are running simulations at Reynolds 240 with a grid resolution of 48 points per chord. The chord is this length in here, which is the maximum chord of the blade. This problem typically has 576 times 384 square, okay? Boundary conditions are periodic in the lateral directions, and we have an inlet-outlet configuration for this case. Showing some results. Well, basically, I'm displaying here the time evolution of these degrees of freedom that I was mentioning before. Actually, this is the angular speed of the blade. In this case, this is a single blade rotor, okay? And basically what we do is we depart from a natural autorotation case, and we start, after reaching a steady state, we start inputting a braking torque, okay? Just 1 minute.
You can finish, but...
okay, thank you. And then basically, as we increase this braking torque, which has this shape, is a constant C0 times the angular speed, basically we see that we are decelerating the blade, of course, right? And basically, this is decelerating at up to non-dimensional angular speed 0.4 for a constant 0.7 case, okay? If we look further to the attitude of the blade, which are these coning and pitching angles that I showed before, what we see is that basically as we increase, we are always reaching a steady state, as you see, okay? Basically, as we increase these angles, as we increase the braking torque, these angles start increasing. Basically, the blade is turning towards the stream direction, okay? And typically what we are interested in is looking at this kind of curve, which is the power coefficient curve, okay? In the end, we are plotting it with respect to the tip speed ratio, which is the tip speed rotational velocity divided by the free stream velocity. And we detect that is somehow a maximum here. This is a curve typically seen in the wind energy sector, okay? The CP versus tip speed ratio. And basically we see that there is a maximum, and basically what we are doing right now is further investigate why this is happening. So I'm just showing here some isosurfaces, three-dimensional isosurface vortex structures for these cases, okay? C0, this is natural autorotation, and basically we see as we increase the braking torque, the attitude starts changing, okay? Actually, this, of course, affects the shedding itself and affects the way the wake is shed, right? And basically, I'm gonna stop here because I'm running out of time. Next steps are basically analyze a little bit the flow and why the optimum is for a braking torque of C0 equal to 0.4. Also analyze what happens with more blades, with a turbulent free stream, and if it is possible to analyze the mass and shape of the blades. I leave here some contributions, and thank you all for your attention.